Hey, um, this video contains the solutions for physics so far, the assignment you did over the break, and I'm going to go ahead and ambitiously try to get the first 5 problems into this video, as those are all of the motion problems, kinematics and the like. So, here we go. Number 1. We have an object with a position given 5 plus 2t minus 0.6 t squared. So I could find the velocity function here. I'm just going to go ahead and do this now because I know I'm going to need them. So those are those things. If we wanted to use the kinematics equations, we could, because this is a situation where we have constant acceleration, right? If we have a square, a quadratic position function, that's going to lead to constant acceleration. Excuse me. And let's jump in here and see if we can crank out some answers. Find the object's initial position, velocity, and acceleration. So the initial position, at time 0, would be 5 meters. The initial velocity would be 2 meters per second. Don't forget your units here. And the initial acceleration, well, acceleration is constant. There you go. Part B, at what time will the object come to rest? I think it'd be better to say there momentarily be at rest. It's not going to like come to rest makes it sound like it's going to stay at rest. They're just looking for the velocity is 0. So I'm going to set my velocity equal to 0. That's 2 minus 1.2t equals 0. That's going to happen at time 2 divided by 1.2, 1.67 seconds. That is when it will be at rest. How long after starting does it take for the object to pass the origin? Alright, so we want to know to pass the origin means it would have a position at the origin. So that would be setting let me be consistent here, that would be setting the position equal to 0. And the how long would be the time. So that would be setting the 5 plus 2t minus 0.6 t squared equal to 0. And you could use the quadratic formula if you're really excited about things like that. I'm just going to graph it. 5 plus 2x minus 0.6 t squared, or x squared. And before I hit y, sorry, let me bring this over to the screen. Before I hit y equals, I know I'm only looking for time. I think you could look from time 0 to 10, but I don't want to look at negative times. So, boom. So let's see. Second, to calculate that 0. It's somewhere, I don't know where it is. It's somewhere between 0 and 10 anyway, right? I'm just going to type those in instead of playing the mouse game, and it's right at 5. So I guess that could have factored if we multiplied through or did whatever. But so t equals 5 seconds. That is when it is at the origin. Part D, at what time is the object located 4 meters from the origin? Well, since I have this graph right here, we're looking for where is it 4 meters from the origin. That would be at position 4. So I could go ahead, and I think the easiest way to do that, makes sense to me, would be to graph position 4, and there it is, right? That's when it's at position 4, right? This is time on this axis, this is position, so there's our position 4. Second, calculate the intersection of those, and I only have 2 curves here, so first curve, second curve. Looks like that happens at time 3.77 seconds. And then we want graphs of position, velocity, and time. So position, well, I just had that up on my calculator, right? That's the, looks like this. Velocity versus time, an intercept of 2, negative slope, so we're not trying to be perfect here, right? That would correspond to that if you're keeping score, which you should be. And the acceleration is just a constant, negative 1.2. Right, so typical kinematics curves. All right, how do we do? 5 minutes, not too bad. All right, number 2. Now we're looking at this graph here, and we want the accelerations given in this graph, and the object starts from rest at time 0, and its position, it starts at position 50. So part A, we want the velocity of the object at time 10, time 25, and time 35. I'm going to take a calculus approach to that. The change in velocity, I know that the area from time 1 to time 2 under an acceleration curve is equal to the change in velocity, right, since velocity is the antiderivative of acceleration. And I know that the initial velocity is 0. So if I made these, if I wanted to do 0 to t, minus 0. Now don't go making the fundamental mistake of calculus here. This is 0 only because they said the initial velocity is 0. The initial velocity could be something else. So that's not, we don't get that for free, right? It's only because the initial velocity is 0. All right, so that means I can figure out in part A, what's the velocity at time 10? Well, this area here is 10 by 2, that'd be 20 meters per second, right? When I find area, I'm multiplying units, so I'd get meters per second. And while we're at it, this would be negative, this would be 10 meters per second. Of course, it's underneath, so it would be negative. So that means, excuse me, since my initial velocity is 0, at time 10, it has increased 20 meters per second. At time 25, oh sorry, this is still part A, so let's be clear here. This is the velocity at time 10. This is the velocity at time 25, because there's no acceleration between time 10 and 25. That means the velocity doesn't change, so it's still 20. And then last, the velocity at time 35. Well, I've had an area of negative 10 go by there, so it's going to drop it back to 10 meters per second. Part B, what is the position of the object at those times? So, let's see, how do we want to approach this? There's different ways you could do that. You could go kinematics on this. It's like piecewise constant acceleration, right? So we could just treat those separately. So I know that position is equal to 1/2 at squared plus initial velocity times time plus initial position, right? That's the kinematics equation. If you're wondering where that came from, that's delta x. That's the initial, right? You could put a delta x here and then just keep in mind that it started at 50, right? So the initial velocity is 0, so that means, excuse me, the position at time 10 is 1/2. Let's see, acceleration is 2 here during that first stretch. Time 10, the initial velocity is 0, plus the initial position is 50. So that's 150, looks like. Position at time 25, well, what's happening at time 25? At time 25, it's from 10 to 25, it's cruising at a constant velocity. So when it's going at a constant velocity, then maybe before I write this, I should write that for something going at a constant velocity, velocity is, position is just velocity times time plus initial position. Now it's doing that for 15 seconds after, after it gets to position 150. So the position at time 25, I'm going to do, that's this position, so 15. For 15 seconds, it's going to be going at a constant velocity of 20 meters per second. Times time is going to do that for 15 seconds, and it was already at position 150. That's how I would handle that. That's 450 meters. All right, and then again, I'm going to say here, my position at time 35, it's going to start from here, and now it has an acceleration of -1. So my position, it's going to do this for 10 seconds. I have 1/2 a t squared, right? It's doing that for 10 seconds. And it's doing this new thing for 10 seconds. I know that here we ended up at 150 meters. At here we ended up at 450 meters. Now I'm trying to figure out here. You might stop here. This would be an interesting place to just think about. Do you think that the number associated with this is going to be bigger or smaller than 450 meters based on what we have done so far? Think about that. Pause, please. Please. No, seriously. Pause for a second and think about that, okay? All right, now we're back and we can get the answer doing this. So that is 100 times -1/2 is -50. It's 400 meters. Nope, that's not right. Scratch that, because it should be bigger. And this is why we ask questions like that, because I know that the answer is supposed to be bigger based on what we've done so far. What I was thinking is this. If it's going 20 meters per second, then it keeps going 20 meters per second, and then it is going to decrease in speed, but it's only going to decrease by 10, so it's still going to be going positive 10 meters per second here. So it's always going forward the entire time here. So that can't be right. So I have this, that's my 1/2, oh, I know what I forgot, plus initial velocity is 20 meters per second times time plus initial position is 450. Yeah, I forgot that, sorry. So that's the -50 plus 200, so that's 600 meters. So that's how I would recommend doing those and thinking about those problems. Graph the velocity of the object as a function of time. So velocity starts out 0, goes up to 20, stays at 20, and then goes down to 10. So something like that. And it's piecewise linear, right? Cannot be curved. And when I say something like that, you don't have that much leeway. And then here, if this is, it starts from 50, it has a positive acceleration, starts with a velocity of 0, so it has a slope of 0, and then the antiderivative of this will be a parabola, right? So it increases like this, and then it continues as a straight line, right, with a slope of 20. And then when it gets to here, it's going to start to decrease. So something like that. It's a piecewise function, piece of upward opening parabola with vertex here, linear piece, 20 meters per second for a while, and then downward opening parabola, right? But notice here you can see that it's always going forward. This would be 50 meters. This would be, was it 150 meters? this would be 450 meters, and then at the end it would be 600 meters. Right, something like that. That is position versus time. All right, that one took a little longer. Let's see if we can pick up the pace. Number 3. We have another equation type thing here. We have velocity as a function of time. Excuse me. It's 3 minus 1.5 t squared. This is a velocity function that's quadratic, so we could not use kinematics equations here, because if I wanted to find acceleration, be the derivative of this, notice it's not constant. And if I wanted to find position, well, they say at time 0 the object's position is 0. So that means I could write, since I know about 0, I guess this is one of those awkward situations. I guess I should put an x there if I'm going to do this, right? Because using the variable t twice. Calculus issue there. So that would be position at time t minus position at time 0. I feel like I should write this down. It does, in fact, it is true that this is 0, because they said the initial position is 0. But that's not always true. That's the fundamental mistake of calculus, to think that that's always true. Okay, so that means the antiderivative of our velocity function is, where did it go? There it is. It's 3t minus 0.5t cubed. And then I would have to add that to the other side, but it's just 0. Right? So that's my position function. All right, so having that work done, that should set us up well to answer these questions. Oh, and that actually is the part A. Find the object's positive maximum displacement from x equals 0. So I want to find the maximum displacement from 0. So that's maximum displacement, or distance from 0. So that's the maximum of the position function. If you want to find the maximum of anything, you take the derivative of that thing and set it equal to 0. Well, there's the derivative of position. It's velocity. So I'm going to set that equal to 0 and solve that. It looks like I'm going to end up with t equals plus or minus the square root of 2. And I'm only interested in positive times, so I'm going to get rid of the plus or minus. And then I'm going to think about here, if I made a sign chart starting at 0 of the velocity, what's going on here? This is a downward opening parabola. Here's the square root of 2. The other square root of 2 would have been over here. It's a downward opening parabola. That means it's negative, positive, and then negative again. Negative, positive, and negative again. So this will, in fact, be a maximum, right? Because it's increasing and then decreasing. And they want to know what is the actual maximum displacement. Well, it happens at time square root of 2, but that doesn't tell us what it is, right? We have to go back up to here to get that. So the actual displacement from 0, in other words, position, is 3 square roots of 2 minus half of the square root of 2 cubed is 2 square roots of 2. So 3 square roots of 2 minus the square root of 2. So 2 square roots of 2, you could do that with your calculator, that would be fine, because this is a time after all. So is that about 2.8 seconds, I think? Sorry, this is the position, not time. 2.8 meters. All right. Part C, find the object's acceleration as a function of time. That, I think we already did. We did. Acceleration is just negative 3t. And then D, draw graphs of velocity and acceleration for the motion of this object? Well, acceleration, sorry, velocity first. It's a downward opening parabola. Kind of know some stuff about it already. V versus t. We know that it would start at 3, and it has a maximum at the square root of 2, so it does something like this. Right? Actually, that's not true. The position function has a maximum there. This has a maximum here at 0, right? So, I'm just going to scribble on that, sorry. It actually looks like this. And this, we know that's where the velocity is 0. That's how we got this, right? Setting the velocity equal to 0. That happens at the square root of 2. Sorry about that. And then the position function would have a maximum there, right? And then acceleration versus time, negative 3t. So that is just a straight line, looks like that. All right. Number 4. Boy dives off a cliff with a running horizontal velocity of 8.6 meters per second. The distance from the edge of the cliff to the surface of the lake is 12 meters. That's the vertical distance. So this is just a projectile motion problem, right? How much time will it take for the boy to fall from the edge of the cliff to the surface of the water? So we have our vertical part, that's all we're interested in here. His initial vertical velocity is 0, because he's launching himself horizontally, right? So what's the vertical part of that initial velocity vector? Nothing. It's 0. His acceleration would be negative 9.8 meters per second squared, or negative g. And his delta y, he's going down 12 meters. That sign is important. It's going to mess you up if you don't have that. And I want to know how long does it take. So I'm going to use the equation that relates these variables. So that is the equation delta y is equal to 1/2 at squared plus vit. In this case, the vi is 0, so I have delta y is equal to 1/2 times negative 9.8 t squared. So my time is, let's see, multiplication of 24 divided by 9.8. I want the square root of that, 1.56 seconds. You could solve that by graphing if you wanted to. There's other ways to do that. Part B. How far from the cliff will he strike the surface of the water? Well, for his, in the horizontal direction, his horizontal velocity is 8.6 meters per second, and he's going to be going that fast for 1.56 seconds before he hits the water. So his displacement is just the product of those, which is, there it is, it's still there, times 8.6, about 13.5 meters. You might think about why it would be rather absurd to include more significant figures here. We're talking about where the boy hits the water, right? So if you're measuring where somebody hits the water when they're diving in, you think you could be accurate to more than the nearest tenth of a meter? I don't think so. So let's see, what's the landing velocity? Well, the landing velocity, I'm going to assume here that since it says velocity, we want both magnitude and direction. I guess you could give it in component form too, but there's going to be a vertical and horizontal part of this. The horizontal part, of course, is just this, right? That's constant. The vertical part, we know that, let's see, the initial vertical velocity is 0, the acceleration is negative g, the displacement is negative 12, and the final velocity I would like to know. So this would be the equation, this must be a question mark, sorry. Vf squared is equal to Vi squared plus 2a delta y. So Vf squared is equal to, that's 0, that's 2 acceleration delta y. So it's the square root of that. 2 times 9.8. Those negative signs will cancel, so I'm not going to bother with them. So about 15.3 meters per second. Now this was a square root, so it would be plus or minus that, right? Now he's going down, so I know that in this case the final velocity that I'm interested in is the negative version of that, right? Now that means that when he hits the water, he's going 8.6 meters per second this way and 15.3 meters per second this way. So you could say his final velocity is 8.6 I minus 15.3 J meters per second. Or you could say that it is the square root of 8.6 squared plus 15.3 squared. You could say that it's 17.6 meters per second at a tangent inverse of 17.6 over 8.6. Oops, just kidding. 15.3. Rise over run, tangent inverse, rise over run. And just make sure we're in degree mode. We are about 60.7 degrees or 61 degrees below horizontal. Right? So I think either one of those would be okay. What's not okay is to just say that this is the final velocity. That's not the final velocity. That's the vertical component of the velocity. So he's going, this boy, in the horizontal and vertical directions. So you got to include both of those parts. All right, let's just do 5 because we're almost there. So number 5, we've got a cannonball fired from a cannon located at the edge of a 35-meter tall cliff. The initial velocity of the cannonball has a magnitude of 540 meters per second at an angle of 42 degrees above the horizontal. So more kinematics here. How much time is required for the cannonball to reach the ground? So that's a vertical problem again. The initial velocity is 540 times the sine of 42. That's the vertical part. The delta y is negative 34. The acceleration is negative g, and I want to know time. So same deal as before. I'm going to use that same equation. Negative 34 is equal to 1/2 a t squared plus vi t. Now, oops, what did I do? Sorry, that's not the vi, is it? That's 540 sine 42 times t. Now that's some nasty looking thing, so I'm going to graph that to find where it's equal to 0. So I'll just move that to the other side. Positive 34 minus 4.9 x squared plus 540 sine 42 x. And I know I'm looking for, this thing's going to go pretty high. So my window here, I think probably I might have to go further than that. I don't know, 100 seconds? Maybe it's going to be airborne longer than that? That would be kind of crazy. It's not going to go below the ground level, and it's probably going to go a lot higher than whatever the last problem was we were doing. If I'm going to do this by 1,000, I'm going to do my y scale by 100. And let's see how that, I should do this by 10 too. This is, the x scale and y scale, that's how often the calculator makes little tick marks, how it scales the axis. So I'm going to graph that. Woo! Higher indeed. Oh, and it came back down. So anyway, I got my result. It looks like it crossed somewhere between 70 and 80 seconds. So I'll find that 0. And it's between 70 and 80, but it's definitely on my screen between 0 and 100, just to be very conservative about it. 73.8 seconds. And how far from the cliff will the cannonball strike the ground? Just like in the last problem, that's the horizontal part of the problem. Horizontal velocity is 540 times the cosine of 42. I now know the time, so the horizontal, the displacement is 540 cosine 42 times 73.8. That's far. 29.6 kilometers. You might wonder to yourself, would a cannonball really go that far? In the absence of wind resistance or air resistance, if you could get it going that fast, then indeed it would go exactly that far. All right. Let's see, what do we have to do next? What's the maximum height reached by the cannonball? There's different ways of doing that, but since I have a graph of this is the vertical stuff going on here, I'm just going to, let's see, what was my window? My y max. Let's go ahead and tack another 0 on there and take another look. I can find the maximum height just by looking at this graph. Right? There it is. So maximum, let's see, it happens definitely between, let's say, 0 and 50. So 0 and 50. So it happens at this time, and that is the actual maximum height. So let's say 6,700. Or about 6.7 kilometers. Part D, what's the landing velocity of the cannonball? I'll let you go ahead and figure that out yourself, just like we did in number 4. But I will tell you this, it's not very much more than 540 meters per second. It might be like 541 meters per second. Why is it so close to the launch velocity? Well, the launch velocity is, if you think about the symmetry of the parabolic path that this cannonball is going to follow in the absence of air resistance, the velocity at any of those symmetric points would be the same, right? The direction would be opposite. And compared to this height that it's going to go to, the 34 meters that we launched it from to start with is negligible. So the extra amount of velocity that's going to pick up for having dropped 34 meters is really small. In fact, maybe we could just do a really quick energy before and energy after. So at the start, I have mg h initial plus 1/2 mv squared initial, and then that's when it gets to the ground, it's going to be all kinetic, right? So it's going to get that much of the gravitational potential energy is going to be added in. But this is so small. So if we make this calculation, we can cancel the masses out. This is going to be 9.8 times the initial height. Oh dear, you can't see that, can you? There we go. Right, so that's the potential energy at the start. It's got 34 meters worth. Kinetic energy at the start, it's got 1/2 m's canceled out. V squared, and then on the other side 1/2, whatever the final velocity squared is. So what's going to happen is this is so much larger than that when I knock out the 1/2 and do that business, we'll just crank that out real quick so you can see what happens. It's really close to 540. So let's see. I'm going to do a bunch of steps at once. You could break this down if you want. 2 times 9.8 times 34 plus 1/2 times 540 squared. 540.6. So it did not make much of a difference. To significant figures that would probably be keeping track of, we wouldn't even notice the difference. And then E, draw all the graphs. So let's do the X graph. So position versus time starts out. Right, position versus time is going to look like that. There's the height. I'm exaggerating. This would be like much higher, right? The velocity versus time. The initial vertical velocity is, and that would go with that. It's positive, and then that line would have a slope of negative 9.8, and the acceleration is just negative 9.8. In the vertical direction, I have, oh dear, sorry, these are the verticals, aren't they? I did the verticals first. In the horizontal direction, I have constant velocity. So what happens there, it starts at position 0 horizontally, and it just goes forward with its constant velocity. A constant velocity. And of course, if you have constant velocity, you have no acceleration in that direction. So there's those graphs. All right, that's video number 1.